Hey guys, Miss Marissa here, and in this video we're going to be talking about Ksp and the common ion effect. Now, what this involves is having an insoluble ionic compound, one that technically dissolves only a little bit, makes an equilibrium, and we're going to be putting into it a soluble ionic compound, one that dissociates completely, and the two compounds are going to have an ion that's in common between them. And what happens is having that ion in common causes some shifting to occur in the equilibrium salt. So what we first need to do is refresh our memory on how can we tell if a salt is soluble or insoluble. College Board wants us to make sure that we know that all group 1 ammonium and nitrate compounds are soluble. If you see an ionic compound with any of those three things into it, we know that that's going to completely dissolve. However, there's other soluble compounds that don't fit those categories, and so we want to have another way of being able to tell whether or not they're soluble. So College Board might give us some sort of clue to help us know about the solubility information of a substance, and one of the clues that they could give us are Ksp values. So to kind of see this in action, you notice down here there's a chart that has 3 compounds in it. We have silver chromate, silver nitrate, and potassium chromate, and they've given us some Ksp values for them. Now, as a reminder, Ksp is an indicator of how much solubility is taking place. If a Ksp is really big, then that means a lot of product is being formed, a lot of ions, whereas if a Ksp is really small, that means only a little bit of it is making product, that most of our ionic compound is staying together. So if you notice here, these bottom two have really large Ksps, but if you look at the types of compounds we have here, that should make sense. You notice that this compound has a nitrate polyion in it, which means we know that that compound is soluble. And this other compound here, the K2CrO4, has potassium in it, which is in group 1. So again, that would mean that it's soluble. And so having those large Ksps makes sense because we're showing that it's basically completely going to the product side. It's completely going to ions in its dissociation. However, this Ag2CrO4, this value being really small, would indicate that that's an insoluble compound. So kind of as some guidelines that you could use to help you with this information, if you see a Ksp that's typically less than 1, so like here 1.2 times 10 negative 12 is really less than 1, then that is pretty much telling us that, hey, we have some sort of salt that's insoluble. Whereas if the Ksp is much larger than 1, then that is indicative of a soluble ionic compound. So giving us Ksp values is sometimes a way of telling us, hey, here's a soluble ionic, but here's one that's not soluble. Also, if you ever have a compound where they do give you a Ksp value for it, and then another one where they don't give you a Ksp value, the one that they do give you a value for is typically the insoluble one, whereas the one that they don't give the value to you, we would assume that that is our soluble ionic. So again, large Ksp value is indicative of a typical soluble ionic compound. We assume that it's essentially going to completion, so it essentially dissolves completely. And because we're making that assumption, instead of setting up a traditional Rice table equilibrium calculation, we can instead just use stoichiometry to do any kind of calculation with it. We could use mole-to-mole ratios to figure out our concentration of our ions after the dissociation has happened. And we'll see that process here in just a few minutes. Also, kind of as a throwback, as a reminder, these would be broken up in a net ionic equation. So you would want to take the compound, split it into its ions. And also, because we're making lots of ions, we would conduct electricity when it's dissolved. However, if we have a small Ksp value, that's going to be an insoluble ionic compound. These compounds only dissolve a very small amount. However, it is not enough that it is considered a significant process like in a reaction. So that's going to play a role here in a minute. So we would use an equilibrium calculation, some sort of Rice table, Ksp value, to calculate any kind of concentrations of our ions that we would have. So because it's not a major player in a reaction, we would not be broken up in a net ionic equation. We would leave it together as a precipitate. Okay. Also, it would not conduct electricity when it dissolves. Yes, we're making a few ions, but it's not anything significant enough where we would be able to conduct that electric current. So we have to be really careful with those. Yes, we're dissolving them for equilibrium purposes, but most of the time we would leave them together as the compound, and we would say that the amount of ions is so small that it's negligible. All right, so down here are some guidelines for performing some of these calculations for common ions. We're just going to kind of jump into the calculations here. So if you get stuck on a problem and you want to use these kind of as some guidelines, you're more than welcome to. But I want to go ahead and jump into our first calculation here. And what it wants us to do is determine some molar solubilities of a saturated solution of silver chromate for each of the following scenarios. So on each of these, we're going to have silver chromate dissolved with some different things. So this first one is just in water, and then on some of these other ones, we're going to be adding it into another solution and kind of seeing what the effect is. So honestly, this first question here that they're asking us about is not any different than what we have already done with Ksp. It's just a general calculation where we are finding molar solubility. So I see, hey, they're giving me a Ksp value. I see it's incredibly small. So therefore I know this is an insoluble ionic salt. And so the only way I can calculate with this is if I set up a Rice table for equilibrium. And so my reaction would be my Ag2CrO4 starting off as a solid. I'm going to do my double arrow here. We're going to make 2 silver ions and 1 of our chromate ions. Don't forget to be putting those charges with our ions. If you have a dissolving equation and you don't put ions or the ionic charges with it, then technically it would be counted wrong. So just be really careful that you're putting those charges there. I'm also going to go ahead and write my Ksp expression to kind of see what information I might need from my Rice table. I know that the solid does not get included, so I'm not going to have anything in the denominator, but the numerator will have these 2 products raised to their coefficients. So I'll have Ag plus 1 raised to its exponent of 2 because of the 2 coefficient there. And I'm going to have this CrO4 negative 2. Okay, so now let's talk about what we're trying to solve here. What they really want is molar solubility. And as a reminder, molar solubility, that is how much of this ionic compound that we have here is dissolving. So really what we're looking for here is the loss of that silver chromate, how much of it is actually dissolving into ions. However, because silver chromate isn't in this equation, we're going to have to use the ions to figure out what's happening there. So I don't really care about the initial and ending concentrations on the silver chromate because I'm not calculating with it anyway. But I do care about these 2 ions. Initially, these 2 ions in this situation would both be 0. I'm starting off with just water, so I don't have any of those ions to begin with. Then this silver is going to go up by some 2x value. Again, the 2 because of the coefficient. So at the equilibrium, I'll have a value of 2x. This guy will go up by just x. Again, I'm maintaining that 2-to-1 molar ratio here. And so at equilibrium, that'll just be a value of x. So now when I plug in this information to the Ksp along with the Ksp value, that gets us 1.2 times 10 to the negative 12. The Ag plus 1 was 2x, which will be squared, and the chromate was x. And if I do a little distribution rearrangement here, 2 squared is 4. And then the x I'll have squared times another x, and so that'll be x to the 3rd. And so in order to solve what x is, I would divide both sides by 4, and then also I would cube root both sides. And remember, cube rooting is the same as raising it to the 1/3. And when I go through that math, that gets me an x value of 6.7 times 10 to the negative 5th. Now let's pause for a moment and think about what we have solved here. Yes, we've solved some information about these concentrations, but most importantly, I have solved the value of X, which is the molar solubility here that I was looking for. So this is the molarity of Ag2CrO4 that would dissolve. It's how many moles would dissolve of that compound in 1 liter of water. Okay, so now that I've solved that, let's talk about the concentration of the ions, because that's the other thing that they ask us to solve here. They want us to solve the final concentration of all the ions. So the first ion we'll talk about is the silver. And I noticed that the silver has a value of 2x. So if I take this 6.7 times 10 to the negative fifth and I multiply it by 2, that gets a value of 1.3 times 10 to the negative fourth molarity. So then the chromate is the other ion I have here. That has a value of just x, so it's going to still be that 6.7 times 10 to the negative fifth molarity. And there's my concentration of my 2 ions. You notice this is the same exact problem like we've done on Ksp homework up to this point. But now let's do something a little bit different. I'm going to talk about what this would look like in a beaker of water. So I have my water here. What I would do is I would put that silver chromate in there. Now remember, this is dissolving very little. Okay, this is a really tiny amount. So what that means is I'm putting in a lot of the silver chromate and only a small part of it is dissolving. So what that means is the bulk of the silver chromate is going to be sitting down here at the bottom as a precipitate. Okay. Now, some books might just show this as our beaker because these amounts of ions that I'm creating are incredibly tiny. We could also indicate that they're incredibly tiny by putting, hey, I'm only going to have a few of these silvers and of the chromates. That there's only going to be a few in there. Now, I will tell you this, one other thing to address if you do decide to draw the ions is that we would want to have a 2-to-1 ratio between them. So you'd want to have 2 of those silvers for every 1 chromate. But again, the amount of ions that you're producing is incredibly small, not enough to conduct electricity. So some pictures might not even show those ions at all. One other thing I want to point out is the issue with the particle diagram for equilibrium is that this is not showing the dynamic nature of equilibrium. That because I put a 2-way arrow up here, showing it's at equilibrium, that technically I'm producing product at the same rate I'm producing reactant. Even though to my eyes this reaction looks to have stopped, it really hasn't stopped. Some of these ions are precipitating at the same time that that precipitate is dissolving. There's still change that's occurring in that beaker. So particle diagrams aren't always the most helpful for these processes, but sometimes you will see them used. All right, let's do a calculation that's now involving the common ion effect. We have, again, our silver chromate, our Ag2CrO4, that we already know is insoluble, and I'm putting it with a 0.015 molar silver nitrate solution. And I notice that they have not given us a Ksp for the silver nitrate. And you're thinking, well, why didn't they give us that? Well, it could be because it's incredibly large, and so I really wouldn't use stoichiometry to calculate with it anyway. And as it turns out, I noticed there's nitrate in here, which means overall, this compound that they're talking about is a soluble compound, because remember, all nitrate compounds are soluble. All right, so let's actually deal with the soluble substance first, and then we'll talk about the silver chromate. So what I'm going to do here is I'm going to write a dissolving equation for my silver nitrate. And it's going to look very similar, except one big difference. I'm going to put a 1-way arrow on it to show that it's going to completely dissolve into ions. And then I'm going to have my silver ions that are aqueous and my nitrate ions that are also aqueous. Now, I'm going to not do a full-blown rice table for this, but I'm going to kind of show you a partial rice table. Even though this is not equilibrium, we can still kind of use that same thought process to help us organize information here. I know that originally before this dissolves, that I would have 0.015 molarity of that silver nitrate, and that I would be starting off with 0 of these 2 ions. But then I know this is going to totally and completely dissociate into ions, and I would use mole-to-mole ratios to figure that out. So all of this is going away. Because there's a 1-to-1 ratio between these, this will go up to 0.015 molarity, as well as a 1-to-1 ratio here. So this guy will also go up to the 0.015 molarity. Okay. So there's my silver nitrate dissolving. Now let's talk about the silver chromate dissolving. Now the issue with silver chromate is, again, it's a insoluble salt, and so I'd have to use equilibrium to calculate with it. So I know here that I'm going to have a rice table involved, and so we're going to have our Ag2CrO4 solid. We're going to have our same ions that we had up above, the 2 silvers and the chromate. So again, this equation looks exactly like the one I did on the last example here. However, here's the big difference. If you notice, these 2 processes have an ion in common. The silver is what we call a common ion between those 2 equations. So what that means is that this concentration of silver is now affecting this equilibrium process. So when I start plugging in numbers into here, again, we're going to be wanting to solve molar solubility. Again, I don't care about the equilibrium expression for the solid substance. But over here, instead of starting this silver now out at 0, it's now starting at 0.015 molarity. Now the chromate's still starting off at 0, but now I have some silver of this to start off with. So again, just like we saw up above, this will gain 2x, this will gain x, but now at equilibrium, this value will be 0.015 plus that 2x, and the chromate will just be x. So now let's start plugging into Ksp. As we know, Ksp is still the silver squared and the chromate. And so now when I plug into this, I would say, hey, my Ksp value is still that 1.2 times 10 to the negative 12th. I haven't changed temperature, so therefore that's going to stay the same. But now my Ag is 0.015 plus 2x squared, and then the chromate is x. Now, some of y'all might already kind of be picking up on the fact that when I start to kind of square all of this, and I have this term over here as well, things are about to get really messy where I'm going to have some of the x's that have a different exponent than other x's, and they're going to be added together. Meaning that in order to solve what's happening here, I would have to use the quadratic equation. Now, AP, College Board, is not going to ask you to solve any problem with quadratic equation. So what that means is there must be a really big assumption that we can make on this problem. Now, let me talk about the assumption for a minute, okay? As we know, this loss is very small. That Ksp is very small. Very little of this compound is dissolving into ions. What that also means is that these gains are incredibly small. Now, if I have no money in the bank and I find $100 on the ground, I'm going to be pretty stoked about that $100, okay? That's going to make a big difference to me in my bank account if I have no money and now I have $100, okay? So that makes a large difference to the amount of that particular ion. But let's say I'm a very wealthy person. I don't know, Oprah, Jeff Bezos, Bill Gates, you get the idea. And I have billions of dollars in the bank. And I find $200 sitting on the ground. Am I going to notice gaining that $200 that much in my bank account? Nope. If I have $5 billion in my bank account and I add in 200 bucks, my bank account is still going to say, oh, I have $5 billion. I'm not going to tell somebody, oh, yes, I have $5 billion and $200. Like, I'm not going to even bother mentioning that $200. So to this amount, that gain is so small that it's negligible. When that gain is incredibly small, we get to ignore it from our equation here. But again, the reason we get to do that is because our Ksp value over here is very small. We always have to, before we ignore anything for quadratic equation purposes, we always need to make sure our equilibrium constant is incredibly small. If it is, then we're typically allowed to do this. If the Ksp is fairly large, like usually the kind of guideline is 10 to the negative fifth and up, so 10 to the negative fourth, negative third, or even a positive exponent, then we can't make that that assumption here. We can't ignore that change if we have a large Ksp. So just be very, very careful there with when you're deciding to ignore Ksp or ignore the change and when you're not, okay? Now, obviously that simplifies our math quite a bit here. In eliminating the 2x, and that means I have 0.015 squared times the x. So I would divide both sides by the 0.015 squared. And when I divide over the 0.015 squared, that gets an x value of 5.3 times 10 to the negative ninth. And again, if I think about what I was trying to solve molar solubility here, the X. So therefore, this is the molarity of the Ag2CrO4 that would dissolve. Okay. But I also want to figure out my concentration of ions. Now I have to be really careful because I have a few more ions in play here than I did on the previous problem. Obviously, I still have the silver and the chromate. So let's talk about those first. My silver would be this 0.015 plus 2x. However, if you plug in this 5.3 times 10 to the negative ninth in for that x and you double it and add it to the 0.015, basically the number just rounds back to 0.015, especially when you address significant figures. With 2 sig figs, it just rounds back to the same number that it was. Okay, the chromate here is going to just be equal to x, and as we said, x is 5.3 times 10 to the negative ninth. We have to be careful because there's technically one other ion. Don't forget that back up here, we also dissociated AgNO3, meaning we also produced nitrate. Now we've already solved nitrate's concentration. It would be equal to that same 0.015 molarity. All right, so now let's talk about a particle diagram. Here it gets a little more interesting than what we saw up above because I have some ions that I have a lot of and then I have one ion that I have very little of. So yet again, at the bottom of this, we're going to have a lot of that Ag2CrO4. Most of that compound stayed together. However, a little bit of it did dissolve, and so we end up with a few ions of CrO4 negative 2. However, we have lots of this silver and lots of the nitrate because those ions came from that dissolving of the AgNO3, the silver nitrate. So if you were to actually like have a picture where you had numbers of these ions, you would notice thousands of silvers and thousands of nitrate ions in here, but you might only have 1 or 2 of the chromates drawn for those thousands of those other ions. So this is kind of hard to show with a particle diagram because we're not necessarily getting those counts of our ions correct, okay? So just keep in mind that those counts are going to be very skewed. All right, let's do one more problem. We have silver chromate, and this time a potassium chromate solution. I notice again that they haven't given me a Ksp value for potassium chromate, which kind of leads me to believe that it might be soluble. And if I really start looking at it, I'm like, oh, look, there's potassium. I know potassium is group 1, so therefore this is a soluble compound. And so let's deal with him first. I'm going to have potassium chromate. And again, I'm going to have that originally starting off as a solid. And we're going to dissociate that into 2 potassiums and 1 chromate. Now I have to be careful on this one because I notice that no longer do I have just a simple 1-to-1 ratio here. Now I have a 2-to-1 ratio, and so that's going to slightly affect my numbers here. I'm starting off with a 0.015 molarity of this guy, 0 of these. But again, this is a strong one, so all of this is going to go to ions, so this is going to go down to 0 at the end. But here, having a 1-to-2 ratio, this molarity gets doubled for the potassium. So instead of 0.015 molar, we're going to have 0.030 molar here. Now, for the chromate, we do have a 1-to-1 ratio, and so for this guy, we will have the 0.015 molarity. Okay, so then, again, I have this with silver chromate. And I know silver chromate is weak, so I know I'm going to have a rise table involved for this sucker. Okay, so I'm going to have my Ag2CrO4, our 2-way arrow because it was insoluble. I'm going to have my 2 silvers and my chromate. And I notice, ooh, wait a minute. Chromate is in common between these 2 compounds. And so yet again, I notice that if that's in common, this is no longer going to start off at 0. So when I'm starting to fill out my rest of my rise table here, I am trying to solve that molar solubility here. On the silver, I would be starting off at 0, but on this guy, I'm going to be starting off at 0.015 molarity. Okay, so then add the 2x, so we end up with 2x of this at the end. Add the x, so I end up with 0.015 plus x here. Sorry, that's kind of running into my particle diagram, isn't it? All right, so yet again, I'm now going to plug this into Ksp. That equation still hasn't changed. It's still silver plus 1 squared times the chromate. Okay, but now when I plug in, I'm still going to have the same Ksp, 1.2 times 10 to the negative 12th. However, for silver, we're going to plug in 2x squared. Oops, let me do that. There we go. Which would end up being 4x squared if I kind of distribute there. But now over here on the CrO4, I'm going to have 0.015 plus x. Now again, this will give you x squared, but then I'm going to have this plus x here. So I'm going to have some places where I have x squared, and then I'm going to have some places where I have x cubed. Again, things are getting messy with those exponents. I don't have consistent exponents all the way across, and I can't combine them because they're being added. So yet again, this would require a quadratic equation. But yet again, I notice, Ksp, incredibly small. And so that plus x, I get to ignore that change. And again, we're ignoring it because the Ksp is very small. Okay, so now that leaves you with 1.2 times 10 to the negative 12th. Again, this would consolidate here to 4x squared. So kind of be careful there. So I would divide over the 0.15, or 0.015, excuse me. I would divide over 4, and then I would square root both sides. And that would end up solving for x. So we do get here that x ends up being 4.5 times 10 to the negative 6. And again, x is our molar solubility of the silver chromate. So this is the molarity of Ag2CrO4 that would dissolve. Okay, now we're going to talk about all these solubilities here in a little bit. We're going to kind of compare the values for all these examples that we've done. However, I do want to take a moment and talk about the ion concentrations. Okay, we're going to have silver. Well, we notice that silver is 2x. So when I double this 4.5 times 10 to the negative 6, That gets 9.0 times 10 to the negative 6 molarity. Okay. I then also have chromate. Okay. Now chromate, technically I would add on this x, this 4.5 times 10 to the negative 6, but again, that wouldn't change it significantly off the 0.015, so I would just say, hey, I'm going to have the 0.015 molarity. But then don't forget, I technically have one other ion involved. Back up here, I had chromate, but I also had potassium. So we're also going to have potassium ion concentration here at the end of 0.030 molarity. All right, so now that I have all those concentrations figured out, let's talk about what our solution would look like. Again, in this solution, I would have lots of silver chromate at the bottom. Lots of that chilling at the bottom. I would have very few of the silver ions this time. We only made a little bit of those, but I would have lots of chromate and also lots of potassium ions. And really, if I was drawing these out, I would see that I would have double the amount of potassium that I do of the chromate. And again, that stemmed back to the fact that it was a 2-to-1 molar ratio between those. So again, if I had thousands of these ions drawn, I might only had 1 or 2 of the silvers drawn in there. Okay, very little of that actually made. So now I want to kind of compare all of the solubilities that we've calculated thus far. Okay, so if I go back to the previous page, we notice that the original solubility of the silver chromate was 6.7 times 10 to the negative 5th molarity. Then when I added the silver into it, that changed the molarity of the solubility to 5.3 times 10 to the negative 9th. So notice I went from negative 5 to negative 9. Negative 9 is a smaller fraction, and so therefore my solubility decreased, okay? I noticed when I added the chromate into it, in this example, that brought our solubility down to 4.5 times 10 to the negative 6. So again, smaller than the negative 5th that I originally had. So let's make ourselves a statement on here. It asks, hey, what happened to the amount of solubility when a common ion was introduced into the solution? Well, in all of these, once I put that common ion in there, adding the common ion reduced or lowered the solubility of the compound. Now, I want to kind of talk about why not using numbers for a second. Thinking back to everybody's favorite, the Shotley Ace Principle. This whole process is essentially an application of the Shotley Ace Principle. Think about what we've done to each of these scenarios. We originally had a reaction that was at equilibrium, where we had a happy little balance between reactants and products. And what we did on example B and example C is that we added in some product. We added to this product side. So think about what that would do. When I add product in, remember back to the Shotley Ace, what that does is that will increase our value of Q. So now all of a sudden, Q ends up being bigger than K. Yes, we're talking about Ksp, but it's still an equilibrium constant. It's still a K expression, okay? So to lower the Q, so I get back to equilibrium, I need to shift to the reactants. Remember, I shift away from what I add, right? Well, if I'm adding to the product side, I need to shift away from it and shift to the reactant side. Well, the reactants side was the solid precipitate. And so if more of the solid forms versus less of the ions, then that means that our solubility has decreased. So even though we've done all of this math, I could have actually described this whole entire process using Le Shotley Ace Principle. It's kind of crazy to think about how that's coming into play yet again. One other thing it asks us about here says, hey, in the examples completed, the concentration of the common ion introduced was the same. Both times we put in 0.015 of our ion. Here we put in 0.015 of the chromate. Back on example B, I put in 0.015 of the silver. But it says here that one of the common ions had a greater impact on the solubility than the other one. So thinking back to at where we started at 10 to the negative fifth. Adding the silver bumped us to 10 to the negative ninth, okay? Adding the chromate only bumped us to 10 to the negative sixth. So we notice that the silver ion had a greater effect. However, if you look back at your equations for things, both your equilibrium reaction as well as your Ksp, I think you'll find the reason why for that. If you notice back at the reaction, notice that there's a 2-to-1 ratio between the silver and the chromate. There's 2 moles of silver ions for every 1 mole of chromate ions. And so because of that, what happens is in our Ksp expression, the silver gets squared, whereas the chromate doesn't have that. It's just raised to the first. So any changes that you get in the silver are going to be more pronounced in the Ksp because it gets squared. So again, the silver has a larger exponent in your Ksp, and that's why it would end up having a greater effect. All right, so to kind of summarize here, some concluding statements. A soluble ionic compound introduced into a solution containing an equilibrium of an insoluble ionic compound will reduce, if I could spell, reduce the solubility of the insoluble ionic compound if the two have a common ion shared between them. If you add in a soluble ionic into an insoluble one and there's not a common ion between them, then you're not going to see all the same effect. It's only because they shared that common ion between them. So what that means is that you're going to shift more toward the reactant side. And again, the reactant is a solid, so that means more of your precipitate will form when you add that common ion in. Also, one last thing here that we haven't really talked about, it says when two solutions that share a common ion are mixed, the salt with the blank value for Ksp will precipitate first. Well, let me go back here to our very first page. If you notice, that original table we looked at actually had the Ksp values for all the substances that we've looked at in this video, the silver chromate, the silver nitrate, and the potassium chromate. And out of these, the only one that precipitated out was the silver chromate, and it had the lowest Ksp value. So when I'm adding in these other ones, having a higher Ksp means that they're more likely to be product, whereas this one with the lower Ksp is going to be reactant. So what that means is that the salt with the lower value for the Ksp will precipitate first. All right, hope this helped. If you have any questions or comments, please feel free to email me. Bye, guys.